Next, we will have CEO Tobias Dewhurst, the CEO of Kelson Marine. He studied aquaculture engineering at UNH for his doctoral degree, and he is a world-renowned expert in hydromechanics. Please welcome him.
Hi, my name is Toby Dewhurst. I'm an ocean engineer with a company called Kelson Marine. My goal today is to give a perspective from the United States on engineering offshore aquaculture structures. We know that aquaculture can help feed the world, and low-trophic aquaculture, with shellfish and macroalgae or seaweed, can help restore the oceans. But working in the open ocean is difficult and expensive, so we have to answer the question, why should we do aquaculture offshore? And the simple answer for us in the US is there's very little room to do it anywhere else. Here in the US, we have the 9th longest coastline in the world. But if you rank countries by coastline per square kilometer of land, the US is the 170th. Our coastline is relatively flat and provides very few protected locations. And many other users are competing for those sheltered sites. So to do large-scale aquaculture, farmers are looking to expand offshore. Now, there are many definitions of the word offshore. I'll use the phrase exposed aquaculture to describe any site that's exposed to waves from the open ocean, regardless of the distance from shore. In this talk, I'll show a few technologies that are being developed in the US, focusing on developments for shellfish and macroalgae. I'll talk about the engineering methods necessary to design robust offshore structures. And I'll conclude by suggesting a few research areas that we need to develop further to improve our ability to engineer the next generation of offshore aquaculture farms. One example of farmers developing new technologies to expand into more exposed sites is found in my home state of Maine. Here, mussels are traditionally grown on rafts so that farmers can enclose their crops in nets to protect them from predators. As farmers have tried to expand to more exposed locations, they've suffered damage to their rafts and lost crops. One solution being developed is a submersible mussel raft, whose pontoons are ballasted with seawater until the raft is suspended 3 meters below the surface. Similar technology is being used for finfish cages. The submerged raft has a greatly reduced to natural frequency, so the accelerations of the mussel ropes due to storm waves is reduced by up to 75%, and crop losses were eliminated. Now, this technology is more expensive than traditional rafts, and has presented several engineering challenges. But the company operating the rafts reported that the technology increased crop yields by 200%, because the mussels were unaffected by storms. Those submersible rafts are being operated in semi-exposed sites. In fully exposed sites, long liner backbone structures are more common. The farm shown here is being developed at an exposed site off the west coast of the US. To expand even further offshore, others are developing unmoored technologies to grow kelp in the deep ocean. The US Department of Energy's Advanced Research Projects Agency has funded several teams to investigate large-scale macroalgae cultivation for biofuels. In the concept shown here, large arrays of macrocystis are towed slowly by autonomous submarines. The arrays are towed near the surface during the day to maximize photosynthesis, but during the night and during storms, the array is submerged several hundred meters to where nutrients are plentiful. At the beginning of that project, it was uncertain whether macrocystis could survive at great depths. But experiments off the coast of California showed that not only can the macrocystis survive this type of depth cycling, but the depth cycled kelp actually grew better than the control group in the experiments. With so many emerging technologies, we need rigorous ocean engineering for offshore aquaculture. We need to design for survival, but also to minimize crop loss in storms, to handle predators and avoid entangling animals. We need to design safe navigation and operations, and ultimately we need to be able to engineer these structures for maximum economic sustainability. Balancing all of those requirements is extremely difficult. I'd like to describe 3 steps necessary to successfully navigate these engineering challenges. Those steps are: identify the requirements, evaluate the system's structural behavior, then design and optimize the economics. To identify structural requirements, we start by quantifying the extreme expected wind, wave, and current conditions. We gather historical data for the site and identify extreme events. Then we can fit those data to extreme value statistics so that we can extrapolate to 50-year or 100-year storms. The next step, and one of the most difficult, is to evaluate the structure's response to those extreme storms. The hydrodynamics of flexible structures are complex, and it's easy to significantly overpredict or underpredict structural requirements if you use overly simple estimates. So we need accurate, practical numerical modeling techniques for these structures. And I'll give an example of how we've developed such techniques for macroalgae farms. At Kelson Marine, we're working with the U.S. Naval Academy, the University of New England, and Kelson Consulting to develop a validated tool for predicting hydrodynamic loads on large macroalgae farms, funded by our Department of Energy's Advanced Research Projects Agency. To develop a modeling tool for macroalgae farms, we first measured the mechanical and geometric properties of real kelp species, then built physical models of the kelp and tested them in a combined wave and tow tank. From that data, we derived hydrodynamic coefficients, from which we construct what's called a dynamic finite element model. What that means is we break every part of the farm, the kelp, the lines, the buoys, into small, finite elements. And at each instant in time, the software tool solves for the forces on each element and integrates those forces to compute the entire farm's response to waves and currents. We can then build finite element models of all kinds of farm designs and subject them to the maximum expected waves and currents for a particular site. We can predict things like the maximum tension in mooring lines, or how far below the surface the kelp sags down when the farm deforms. We can also design for operational considerations like how much force will it take to raise a line to the surface for harvesting. With this model in place, the biggest question for us as engineers was, does this tool give valid answers that can be used to design robust offshore farms? So we deployed a farm at the University of New England site in Saco Bay, Maine, on the USA's northeast coast. The site is fully exposed to the Atlantic Ocean. The design conditions are a 1 meter per second current and a 4.2 meter significant wave height. Once the kelp was fully grown, we deployed load cells to measure the tensions in the mooring lines and, simultaneously, measured waves and currents. We collected data through a storm event, and the numerical model results for maximum tensions almost exactly matched the measured tensions. So we demonstrated this technique can be sufficiently accurate to mitigate the risk of structural failure of moorings, attachments, and growth substrate. We can now look for weak spots in the structure, we can analyze failure modes and effects, and design to prevent cascading or catastrophic failure in the event of an accident. The next question was, is this approach practical for informing wide ranges of design choices? To evaluate that, we combined the dynamic model with a simple economic model for an example farm at our exposed site. The economic model included capital expenditures and approximated total biomass yield based on usable grow line length and kelp growth as a function of average grow line submergence. Using a design of experiments framework, we then quantified how various design choices such as line spacing, mooring scope, buoyancy, and mooring line stiffness affect the target metric, that is, biomass per dollar of capital expenditure. And the surprising result was that when we examined the predicted biomass yield in kilograms per dollar of capital expenditure over the design space, we can see how sensitive the optimal design is to choices of line stiffness, mooring scope, and how much buoyancy is installed on the farm. These results suggest that a carefully designed system can perform up to 3 times as well as our original design. And this is all done with simulations that can be run in a few days on a desktop computer. So we now have some confidence that this dynamic modeling approach is not only giving us valid results, but it also has practical applications for designing novel offshore farms and optimizing for economic sustainability. I'll conclude by sharing 3 areas of further engineering research that I think will help aquaculture expand offshore in a sustainable way. First, we need more data on the lifetime of synthetic components in the ocean. This will allow us to reduce inspection and maintenance costs and reduce the risk of structural failure. In the USA, at least, the uncertainty around protections for endangered species is making it difficult to get permits for offshore farms. Up until now, federal agencies have made decisions about the risk of whale and turtle entanglements based on somewhat qualitative judgments. Researchers at NOAA, the U.S. Naval Academy, and Duke University are working on quantifying the physics of whale impacts with aquaculture structures. But to engineer structures to minimize the risks to large marine animals, we need more research into the factors that affect entanglement. Lastly, as an industry, I believe we need to develop comprehensive measures of risk. We presently use safety factors and unique and failure rates that are used in other offshore industries, but we need to re-examine these for the unique applications in offshore aquaculture. We've made great progress as an industry in being able to engineer successful offshore aquaculture structures. I believe each one of these advances will take us a step further toward feeding the world and restoring our oceans in a way that is environmentally, socially, and economically sustainable.